So, I'm actually flattered that so many are still here. Thank you for being here. So I'm Ingemar Fredriksson from Linköping University, where I work as an adjunct lecturer, but actually I have my main employment at Pyramid Instruments in Stockholm. And this presentation, or this study, is a cooperation between Linköping University, Pyramid, and the Beckman Laser Institute, initiated by a sabbatical visit by my colleague, Professor Thomas Strömberg, last year at Beckman Laser Institute. So, I'm going to talk about an evaluation of a multi-layered diffuse reflectance spectroscopy system using some optical phantoms. So, the aim in this talk or in this study is to evaluate the accuracy of the estimated properties in this multi-layered skin model that I will talk about a bit more later. And more specifically, we want to estimate the accuracy of the hemoglobin fraction, the oxygen saturation, the scattering properties, and a top layer thickness of this model. So, the model that is used is incorporated in the Periflex 6000 EPOS system, where EPOS stands for Enhanced Perfusion and Oxygen Saturation. And I will begin this talk with talking a little bit more about this system and the methods that are used in them before I continue with this phantom evaluation. So the instrument is used for microvascular assessment of red blood cell tissue fraction, its oxygen saturation, and a speed-resolved perfusion measure. The diffuse reflectance spectroscopy part of this system works in the wavelength range of 475 to 850 nanometers. The laser Doppler part of the system works at 780 nanometers. It's a probe-based system where we have an integrated probe with altogether 5 fibers, one fiber delivering white light for the spectroscopy part, and that light is collected at 2 distances from that delivering fiber at 0.4 and 1.2 millimeters, and then we have one fiber delivering the laser light that is collected 0.8 millimeters from that fiber. And you can see the small probe here. There is also a heating plate, which you see there. So the system is integrated in this, and we have right now an external white light source that you see on the side here. So we utilize a model-based analysis in this system. So we measure diffuse reflectance spectra and laser Doppler spectra from the same site. We have a tissue model that is really the heart of the analysis. From the tissue model, we have a DRS algorithm that utilizes some pre-simulated Monte Carlo data. From that algorithm can calculate spectra from the tissue model parameters. Those calculated spectra are compared with the measured spectra, and depending on the differences between the spectra, the tissue model is updated in an iterative process until the measured and calculated spectra agree. And the same is done for the laser Doppler part. Laser Doppler spectra are calculated from the model, compared with the measured spectra, and the model is updated. So the same model is fit fitted to both spectroscopy data and laser Doppler data. When we have models that fit as good as possible, we read our wanted quantities directly from the model. In this case, the concentration or the tissue fraction of red blood cells, their oxygen saturation, and a speed resolved perfusion measurement. A little bit more about that. The model is a 3-layered model where we have blood in 2 of the layers. The blood has a certain oxygen saturation that can be varied in those layers. There is a scattering following an exponential decay in the model. The scattering is the same for all 3 layers. There is an epidermal layer that can contain melanin as absorption and has a very varying thickness. And the blood in those 2 layers has a certain speed distribution that is also controlled by some parameters. And some additional parameters that I am not going to talk about right now. As I said, spectra are calculated from the model, and the parameters are iteratively updated until we get something that looks like this, where I hope you can see that there is 1 black curve and 1 red curve in each of these. So this is the DRS spectrum from the shortest fiber separation. This is from the longer fiber separation, where you can see that you have more effect from absorption. And this is a laser Doppler spectrum where you have frequency on the x-axis instead of nanometers on the other ones. So when we have this nice fit between measured and calculated spectra, we simply believe that we have a model that is representing the tissue rather well. An example, measurement example from an ongoing study. This is a post-occlusive reactive hyperemia. So we occlude the upper forearm and the upper arm for 5 minutes, starting at 5 minutes. So you can see that during the first 5 minutes, which is the baseline, we have some variations in oxygen saturation in red and in the red blood cell concentration in blue. When we occlude, you can see that these oscillations stop immediately. Maybe some of you can explain to me why that is. It's interesting to see. And then the oxygen saturation starts to drop quite slowly towards 0% oxygen. At the same time, the fraction of red blood cells in our tissue volume increases slightly. And then when we release the pressure, we get a high increase, fast increase in oxygen saturation. The tissue has built up a need of oxygen. The red blood cell concentration also increases a little bit and then goes back slowly. What we see on the right side here is a speed resolved perfusion measure. So, sorry. The blue line here is perfusion of blood flowing with a speed below 1 millimeter per second. It's wrong in the legend here. So slow flowing blood. The red is blood flowing with speeds between 1 and 10 millimeters per second, and the yellow one is above 10 millimeters per second, and the black one is simply the sum of the other 3. So what you can see is that you have an immediate stop in perfusion when you occlude the forearm. Especially the higher speeds are going down to 0. The lowest speed, you have some motion left there. And you see that this drop is much faster than the drop in the oxygen saturation. Because in the oxygen saturation, you have a diffusion process of oxygen leaving the blood, going to the cells. But here you have an immediate stop in blood flow. And then you see some differences when the blood is and the blood flow is recovering to the baseline. The fastest flowing blood is has the fastest change as well, and not much happens with the lowest speeds. So, coming closer to the evaluation and phantoms, just shortly about how you can evaluate a model-based or any optical method really by using quite complicated Monte Carlo simulations with thousands of individual vessels. You create these models with very many vessels of different sizes, different oxygen saturations and speeds and so on in the vessels, and then you can calculate spectra from these models and compare what your method gets to what you have really put into the model. We have done that, but this talk and this study was more about using tissue phantoms for evaluation. We have heard this PDMS before. So these tissue phantoms are quite similar to what Gordon talked about in the first talk in this session. But the difference is that we have other absorbers in these phantoms. So we have titanium oxide as the scattering agent. We have a thin phantom that is an epidermal phantom where we use coffee as an absorber, quite similar to melanin, actually. And then we have this thicker phantom where we have freeze-dried bovine hemoglobin as an absorber. And that is our try to mimic the skin as good as we can. We made some combinations of these phantoms. So we had 2 dermis phantoms with 2 different hemoglobin concentrations. We had 3 thicknesses of the epidermis phantoms with 3 different concentrations of coffee. So in total 9 epidermal phantoms. And then we combined 1 dermis and 1 epidermal to get 18, and then we just measured on the dermis phantoms as well, so in total 20 different combinations. And we measured on 4 different locations in each of these combinations. The optical properties were measured in these models, again, as Gordon described earlier, so I am not going to talk about those details. But the results was that the absorption of the epidermis, one of the epidermis phantoms, was as the black curve here. The absorption of one of the hemoglobin phantoms were as the blue curve here. We said that this dermis phantom contained reduced hemoglobin, and then we created another absorption spectra, this one, that differed from the blue one as much as the difference between real reduced hemoglobin and oxygenated hemoglobin that are those curves up here. I should also say that the absolute values of these curves are scaled a little bit to better match the absolute values of real hemoglobin. We excluded some data where we had a very low significant signature of the hemoglobin in this area. So if this gray marked area here was too low, we simply excluded that measurement because our method really relies on this the spectral signature in this area. So we done some forward calculations on the measurements when combining, for example, one dermis and one epidermis phantom. We knew the measured optical properties of those phantoms, so we could put those known values in our model, calculate spectra, and that is the red curve here, and compare that with the measured spectra from our system. So we see that we get a quite nice match between the measured spectra and the forward calculated spectra, and that's the first part of the evaluation, really, that these two match. Then we looked at, when running the whole method on the measurements and what they said about the oxygen saturation, the hemoglobin concentration, the epidermal thickness, and the scattering coefficient. We got the result, root mean square difference in the oxygen saturation of 2.9. We expected that the method should say 0% oxygen, and it differed on average 2.9 percentage units from that. The hemoglobin concentration, the relative root mean square difference was 25% for those measurements with the more pronounced hemoglobin signature in the absorption spectra, and the root mean square was less, 11%. The accuracy in determining the epidermis thickness was not that good, and the accuracy of the reduced scattering coefficient was 15%, and you can see the colored curves here are the measured scattering spectra, and dotted here are the estimated. So, I think I will skip this. I think my time is getting out. But I'm going to talk a little bit of the conclusions. The method is designed for measuring the red blood cell tissue fraction accurately and the oxygen saturation accurately. This has affected the method design in the choice of included wavelengths, the way we calibrate the system, how we optimize, how the fitting process is done, how the error function is designed. And the result is that the hemoglobin concentration and the oxygen saturation are quite well estimated. Also, the scattering is quite well estimated, but we have a less accurate estimation of the epidermis parameters that we don't really care that much about in the end. About the phantoms, they are very good for this purpose because they have physiological relevant scattering, they are long-term stable, they are two-layered, so in that sense they are more representing skin tissue than others. A problem is that the hemoglobin absorption is less distinct than real hemoglobin, and therefore our results are getting a bit worse than with real hemoglobin. So I already said it was a cooperation between Linköping University, Paramed, and Beckman Laser Institute, and we got our financing from the Swedish Research Innovation Research Institute, Fulbright Sweden, and National Institute of Health. So, thank you very much for listening.